Okay, this is going to be the first of three videos where I'm going to just, in each of them, I'm going to work through the first derivative analysis for a particular function. The first one is for a polynomial, the second one is going to be for a rational function, and the third one is going to be with a trigonometric function. So this is the first derivative analysis for this function. Remember, what we're going to be trying to do is determine the intervals of increase and decrease, and we're also going to be able to find the relative extrema. So once we have our sign chart done with the number line, we're going to be able to also find the relative extrema, and we'll talk about that when we get there. So the first thing with the first derivative analysis, we're going to find the derivative, of course, and so the derivative 3x to the second minus 6x. Next thing we need to do is find the critical values. And type 1. Type 1 is where the derivative is equal to 0. So we set the derivative equal to 0. And it's not particularly challenging to solve that. We're going to factor out 3x, leaving behind, let's say we have x minus 2 is equal to 0. Is that right? And so we have 3x is equal to 0, or x minus 2 is equal to 0. So that gives us x equals 0 for one critical value, x equals 2 for the second. Type 2 is where the derivative does not exist. Because this is a polynomial, the derivative is a polynomial, we know that polynomials exist everywhere. The domain is all the real numbers. And so there are none. There are no type 2 critical values, and the reason is because it's a polynomial. All right? So these are the only two cut values for the number line. So we're going to take the number line, plot these. So we have x equals 0, we have x equals 2. So this is one interval from negative infinity to 0. The second interval is from 0 to 2, and the third interval is from 2 to infinity. We need to find the behavior of the function in terms of its increasing and decreasing in each of those three regions. So remember, the process is we choose from each of these regions a representative. Now remember, the interval is determined by the cut values, but the behavior of the interval is determined by the representative value. We may choose any value we want. We might as well choose an easy one. I'm going to choose -1 in this interval. I'm going to choose +1 in this interval. And it makes sense to choose 3 in this interval. Any value will do, but you might as well choose easy ones. Now, the next piece is we need to determine the increasing or decreasing of the function in each of those intervals. That is determined by the derivative. So, take the representative values and evaluate the derivative. This needs to be the derivative at each of these representative values. First at f prime of -1. This is the derivative we're using, the 3x to the second minus 6x. So this is 3 times -1 to the second minus 6 times -1. That's 3. This is +6. This is 9. The fact that it's 9 is not the important piece. The fact that it's important is that this is bigger than 0. If the derivative is bigger than 0, that means we know the function is increasing in that interval. And now we have the same song, 2 more stanzas. And so we need the derivative evaluated at 1, the next representative value. 3 times 1 squared minus 6 times 1. That gives us, what do we have? 3 minus 6 is -3. All we're concerned with is the fact that that's less than 0. If the derivative is less than 0, that means the function is decreasing in that interval. And then we need the derivative evaluated at 3, the last of our representative values. 3 times 3 squared minus 6 times 3. Uh, 9 times 3 is 27. 6 times 3 is 18. 27 minus 18 is 9, which is greater than 0. So the function is increasing on that region. So we know where the function is increasing, we know where the function is decreasing. Increasing on the interval from negative infinity to 0, decreasing on the interval from 0 to 2, and increasing again on the interval from 2 to infinity. So I'm going to write that out just as those solutions. So this determines the first piece, which is the intervals of increase and decrease. So f is increasing on from negative infinity to 0. And remember, we are expressing our intervals as open intervals. And the next increasing is from 2 to infinity. And then we have f is decreasing on the interval from 0 to 2. So that's the first piece. We've determined the intervals of increase and decrease. Now, notice the curve is going uphill from negative infinity to 0 in this interval, and then changes to going downhill. That must mean at some particular point, you must have reached the top of the hill. And then similarly, this is going downhill. This is now going uphill. Somehow you must have hit the bottom of the valley. So this is the top of the hill, and then this is the bottom of the valley. This point now is, if it exists on the curve, if there is such a point, then that point would be a relative maximum. And if this point exists on the curve, this would be a relative minimum. And since we know this is a polynomial, we know that point must actually lie on the curve. The only reason this might not be a relative max or a relative min is if the function is not defined there. So we need to find one last piece. We need to find the coordinates of that point and the coordinates of that point. We need to find the coordinates of the relative maximum and the coordinates of the relative minimum. The relative maximum we know occurs when x is equal to 0, if it actually exists here. So the maximum is going to be at 0, comma, and we're going to find that number. This is a relative maximum because this is not necessarily the absolute maximum of the function. And then we also have a potential relative minimum. Again, this is, until we actually find the number, this is a potential minimum. That will occur at 2, comma, and we need to find that value. Now, the last piece is this. One of the very common errors students make is using the wrong function in the wrong spot. So, determining the arrows going up or down, that's what we use the first derivative to find. Once you find where it increases and where it decreases, the first derivative has done its part. It no longer takes a piece or a position in this problem. To find the actual coordinates, use the original function. The original function is used to find points on the curve. So to find the relative max and the relative min, use the original function. The derivative is only used to find the arrows up, down, increasing, decreasing. But once you've found those increasing, decreasing pieces of information, then the first derivative is no longer used in the problem. We now need to find the coordinates of that point on the curve. To find points on the curve, use the original function. So, we need f of 0, and we need f of 2. These values, we're going to find these y coordinates. Well, f of 0 is not particularly challenging to find. So this is going to be 3 times 0 squared, 3 times 0 to the third power minus, use the correct function here. I'm going to use the function, this is 0 to the third minus 3 times 0 squared plus 4 is 4. And then f of 2 is 2 to the third minus 3 times 2 squared plus 4. And we need to actually compute that. That's 8 minus 12 plus 4. I believe that works out to be 8 minus 12 plus 4 is 0. So we have 2 comma 0 and 0 comma 4. So we have increasing negative infinity to 0, increasing from 2 to infinity, decreasing from 0 to 2. And then we have a relative maximum at 0 comma 4, relative minimum at 2 comma 0.